Welcome to Module 2 on Preliminary Engineering and the Owner's Consultant Oversight of the Milton-Madison project. We're pleased to introduce our speaker, Aaron Stover. Aaron is a structural engineer and project manager with Michael Baker International in Louisville, Kentucky. Aaron has been involved with the inspection, design, and rehabilitation of many long-span bridges over the Ohio River and other navigable waterways. He has served as Michael Baker's project manager for the Milton-Madison Bridge project since 2008, leading the bridge type selection process and development of the plans and special provisions for the design build letting. Aaron continued his role as project manager, overseeing the design review and construction inspection of the project. Aaron?
Thank everybody for attending. It's an interesting project, one that I've had the great privilege of being involved with since 2008, as Mary Lou said there earlier. So with that, I'll go ahead and kick this off and tell you a little bit about the project. I'll go through a little bit of an overview. There'll be some overlap with what Kevin and Ann presented earlier on the environmental study. We'll talk in more detail about the peer assessment, preliminary engineering, including the peer rehabilitation concept and SCAR countermeasures. Briefly touch on those contract requirements again, and then talk about our role as the consultant oversight and design review function for NDOT on this project. Just to refresh everybody's memory, the challenge here really was to replace a sick bridge. We had an 80-year-old bridge, very narrow structure, structurally deficient, functionally obsolete. It was in need of replacement. When we got started with this project, it was basically not long afterwards that it was posted for 15 tons, which really created a sense of urgency about this project and really a sense of unified action for the local communities that saw the short-term nature of this bridge and how it would not necessarily be around for a long time to come. So with that in mind, we kicked off our environmental process back in June of 2008. This was part of our bridge type selection and environmental. Through the course of that, very early on actually, we had a Kentucky Partnering Conference, which was held over in the Lexington area in August of 2008. And a speaker there from the state of Missouri came and spoke about the Superstructure Replacement project that they were doing on a much, much smaller scale, which really got the entire project team sort of aware of the solution, aware of the possibilities, and we started asking the questions, could this be applied on a much, much larger scale like an Ohio River bridge? So that led to the ultimate peer evaluation in January of 2009. But, you know, we didn't really know if this was going to be something that would pan out, so we had to keep two tracks really operating. We had the environmental track working. At the same time, we were looking very strongly at this superstructure replacement, which was eventually merged into the environmental process as well. We knew the superstructure replacement had a lot of potential for lower costs and less impacts to the historic district, as Kevin mentioned. And then, you know, again, in this timeline, around April, May 2009, we developed our final alternatives, and superstructure replacement was one of those, for sure. By August of 2009, we had a proposed action that was superstructure replacement. In September of 2009, submitted the application for the Tiger Grant, and then in January rolled that into an RFC submission to Indiana so they could advertise that for letting and for construction. So that kind of gives you an overview of the environmental and preliminary engineering time frame. Again, just to rehash a little of what Kevin spoke to earlier with the environmental process, we looked at a whole slew of alternatives up and down the river. After we had received the public input, I think we were up to about 16 different options that we were looking at. You can see a couple of different bypass options out both the east and the west, and then a number of options downtown as well. We even had one gentleman in the public suggest that we build a tunnel underneath the Ohio River. So that was one of the ideas that was considered and eventually dismissed as well. One other thing to point out on this slide is the proximity of the bridge, which is shown kind of in this purple color right here in the center of the screen. That bridge was basically in a historic district at each end, touchdown at each end, and then it was right along the edge of the National Historic Landmark District, which is Madison. I believe Ann touched on that earlier with the significance of that community. Certainly couldn't really be understated. So that drove a lot of the decisions in the environmental process, as you might imagine. The bridge alternatives that were considered, do nothing. Obviously, that was a very short-sighted decision, and we knew what the outcome was going to be, which would lead to bridge closure and certainly impacts to the communities there as well. Rehabilitation, again, I mentioned the bridge was posted at 15 tons. The states had dumped a lot of money into that bridge, as Kevin mentioned before, and the prospects of continuing that maintenance schedule was not a well-received thought either. We looked at a number of different bridge replacements up and down the river. One of the stipulations that the M3T team brought into this was that Kentucky and Indiana were only going to maintain one bridge at this location in the future. So, if we did do a bypass alternative, the downtown bridge would eventually be demolished, which would leave the community with a runaround, so to speak. There was a lot of concern in the community about this because they felt like if you bypassed the downtown, that potentially that could have economic impacts to Madison and essentially, eliminate people from coming downtown. So there was a lot of concern about that as well. They wanted to keep that bridge fairly local, and that's really how the two communities act. They're two communities, but they act as one, just separated by the Ohio. And then obviously we considered the superstructure replacement as well. This was really a potential game changer for the project team. We knew there would be lower costs involved, less impacts, but we really had to answer the question as to whether or not this was a real feasible approach to this project. So here you see our refined alternatives being narrowed down to basically 5 here. We've got a couple different bypass options to go around the historic district, which is outlined here in green now. Superstructure replacement, which is along the existing alignment. And we looked at 2 variations of that. One that was basically the limits of the bridge, a strict bridge replacement, and then the other purple outline that you can see, which kind of tied in and improved some of the approaches. So we had a minimal approach and a larger project as well that were considered. We weighed the pros and cons of that superstructure replacement against the other projects. Really, one of the keys that was mentioned earlier was no right-of-way was involved in that. Less time, span length could be maintained. Again, a 727-foot span versus a 900 or 1,000-foot span as mandated by the Coast Guard meant savings in cost there as well. Projected at about $50 million savings against some of the other alternatives. A lot of that was due to right-of-way acquisition and additional approach work. Much of what's in Lower Milton is in the floodplain, so there were certainly concerns there with building approaches up out of the high water. But one of the biggest cons against the entire project was the 12-month closure that Kevin mentioned. We knew if we took that bridge offline for that length of time, that was going to be a major thing. So the 2 states really stepped up and committed to that 12-month closure as a maximum there. Tiger Grant was definitely a pro. Being able to demonstrate that we could get this project off and running and be eligible for a Tiger Grant was another thing in the pro column. So you've seen this slide before. This is essentially the superstructure replacement. Again, not widening the navigation channel. That 727 feet is a key cost saver there. And then you see the 4 piers that were proposed to be strengthening of the existing pier, and then obviously widening of the pier cap since we were supporting a bridge that was twice the width of the existing. The overall project timeline. This graphic is really kind of a melding of what KYTC's typical project timeline is. They were the lead in the environmental process, and you can see the top bar there kind of illustrates what a typical project of this nature may take, spanning as many as 13 years. We really condensed the Milton-Madison project down and accelerated all phases of it. Not only was the construction accelerated through the use of design-build contracting, but we also heavily condensed the environmental process. We managed to get that done in about 18 months, which is pretty remarkable for a bridge this size and a major river crossing with a couple of owners and a lot of stakeholders involved. So we really pushed that through, and I think the superstructure replacement helped to do that as well. Certainly, it was very important to get the community buy-in to head that direction, and the fact that we had a thick bridge really got everybody going and pointed in the right direction. You can see overall a potential 4 to 6 year reduction was what we were projecting early on with the 2013 completion that was advertised. Kevin mentioned earlier the goals for a successful project for NDOT, and these were really the conditions that we were working under in order to get this project off to letting. We had to make sure that it could be designed for a 75-year service life, that it was in fact feasible, and that was vetted out through that Pier Strengthening report he mentioned before. We also had to come up with a scenario to construct the bridge within the 1 year closure that was mandated or committed to. Had to be formidable. It had to be, the U.S. Coast Guard had to buy in on it as a sponsoring agency, and it had to be visually acceptable. We spent a lot of time working with the local community to make sure that they were, in fact, in favor of this bridge that was being constructed. We worked with them, as Kevin mentioned, to stipulate the appearance of the structure as well as the railings and finishes on a number of different components throughout the structure. I'll walk you through now this next portion. We'll talk about the pier strengthening concept that was contained in the contract documents. And really, this is the basis of it here. We've got the existing pier shown on the screen right now, and you can see how it tapers down as it goes up in height. The existing truss was 24 feet center to center of chord with a 20-foot wide roadway. And as Kevin mentioned to you before, we were going to widen that significantly. The thought was to do that basically under traffic with the existing bridge still in service, to come by and put an encasement around this pier, widen it out at the top with a wider pier cap, and then come back, demolish the existing superstructure, and during that 12-month closure, then finish off the pier caps and put in the new wider superstructure, which would be roughly twice as wide, with a 40-foot travelway and a 5-foot pedestrian walkway out hanging there. Now, those existing river piers were really, unreinforced section, largely. When we started looking at this and looking at the existing plans, they're comprised of an existing pier stem. That pier stem is, I'll say, mildly reinforced. It's minimally reinforced, and then that sits on top of an unreinforced caisson. Caisson extends through about 20 feet of water and 60 feet of soil, and is eventually socketed down into rock anywhere from about 2 to 6 feet into that rock there as well. There was a small layer of boulders that was encountered during some of the drilling at the bottom, making any additional or any other foundation stabilization techniques a little bit more challenging there as well. But that's basically the cutaway of the existing river piers and what we had to work with to start with there. To further our understanding of those existing piers, we wanted to take a closer look at what the methods were that were used to construct those. So we did a little historical research as well, and we found this old photograph of the construction. And essentially, this was one of the piers near the shoreline that they had built a steel cofferdam and then rolled that out into place into the river. So that process is kind of animated here. This is showing for one that would have been floated into place. They had this caisson chamber that would have been floated out and then sunk to the bottom of the river. You'll notice the two tubes on the top. Those are basically airlocks. Essentially, workers went down in those airlocks, excavated the material out. It was lifted out and removed. And as they excavated material, they kept piling more and more weight on top of the structure, which eventually would sink it down through the mud and through the river bottom. Workers came out and they filled that entire chamber with concrete, and then finished off the upper sections by pouring the first section of the pier stem, removing the formwork, and then the pier is essentially complete. So, Kevin touched on this earlier as well. One of the first tasks that we needed to do to determine if those piers were capable of being reused was obviously an engineering analysis. We sat down with pen and paper and really went to work to figure out if it was even feasible from an engineering standpoint. Seeing some hope on that horizon, and a lot of interest from the stakeholders involved, KYTC set about doing some vertical coring on the piers. This is really the best way for us to gather the information needed, both from a soil borings perspective and also from an internal quality of the piers perspective. So initially wanting, boring information to understand the rock capacities, Cabinet said, well, we can also get you the information down through the piers by drilling through the deck and through the entire length of pier and then 50 feet into bedrock down below. We did that all in all for four different piers on the job, 6, 7, 8, and 9. And those cores were extracted and tested and viewed and everything else. Kevin mentioned earlier, yes, we did have some of the concrete tested. It was very high strength. Some of it broke as high as 12,000 psi as well. A full workup was done of the exterior of the piers. Obviously, the interior was in good shape with the coring. We did a full workup of the exterior as well. The piers were sounded, hammer sounded, checked for delaminations, spalls, crack widths noted, measured, mapped. They did a full-blown, this was CTL Group, did a lot of this work, did a full-blown workup with GPR and impulse response to determine the properties of the reinforcing within that pier section there as well. And even extracted some samples for both chloride testing and some cores for compression testing and petrographic examination. So all of that work really culminated in two reports. One was a document of the existing conditions, which really outlined all of the inspection efforts that were taken under the bridge. So a full workup of the condition was known. And then the other was a culmination of the laboratory effort, specifically the chlorides and the petrographic analysis to come up with a service life assessment. Now, what came out of that? Well, basically the results were generally good. We had a number of piers, the main river piers, 6, 7, and 8, were in very good condition out there. There was some durability concerns noted. Specifically, there were some issues with paste in the aggregate. A lot of wear from the river had washed some of those the paste away and sort of fines away. So there were concerns about that and how it would behave long term. Also, some of the lift lines had eroded away somewhat. So those were the general durability concerns. As Kevin mentioned earlier, Piers 5 and 9, those were both at the ends of the bridge where there were joints over top of them, and the use of de-icing salts over a number of years had led to really high chloride values, particularly in Pier 5. Pier 5 had some very high chloride values in there as well. Pier 9, not quite as bad. We did end up replacing the entire upper portion of Pier 9, but it was a land-based pier, so not as big of a concern there. But generally good results on the main river piers, which gave us a lot of confidence moving forward. So with that confidence, we then had to take a look and really get to the engineering behind it. We had a number of concerns over the demands. We had a heavier truss. We had increased pier weight if we were going to do this encapsulation. Wind loading was a concern, and larger live loads than previously used. Also, vessel collision was not something that was done back in 1929. They didn't run the kind of barges that they do now up and down the Ohio, so we had to take that into consideration in the pier response as well. We're dealing with the proposed solution, which would have been to encapsulate around the existing pier. We had to work out a detail for how to tie in the new wider pier cap to that existing pier. Concerns over tension in the stem and the interface, which I'll talk more about later, and then tension in the unreinforced caisson and a limited foundation geotechnical design were all part of the pier response concerns that we had to address to prove that feasibility. So we started out with a conventional analysis of the piers. This is basically just your standard spread footing look at it. If you take away all of the soil that's susceptible to scour and ignore the softer soil response of the overlying riverbed, compared to the rock, then you will note that then you'll end up with a essentially what is a conventional spread footer on rock approach to it. So when we did this, we applied the loads, calculated what the eccentricity was, and the results were that the eccentricity was outside of the footprint of the footer, which indicated that it was not good, that the footer could potentially topple over. So we had inadequate resistance at both the strength and extreme limit states, and our course of action then was to really step back and take a look at it. We knew that in the 80 years, obviously the piers hadn't toppled over, so we had to figure out what was going on. How could we refine our analysis to better predict the behavior that was out there in the field? So we set about refining the barge and the wind loads on the model, and then refining the analysis method as well for the resistance. First stab, as I mentioned, refining the barge impact. We had done a preliminary method 1 during our initial look at this, just to get a ballpark for what those barge impact forces might be like. So we saw some value in going back and taking a little bit closer look at that by doing a probabilistic analysis, or method 2 analysis, as permitted by the codes. And in doing so, we saw a 20% reduction over the method 1, which, every little bit helps when you're dealing with something that's existing finite capacity. So that was documented, and we moved forward with that. We also sharpened our pencil with respect to the wind loads. We could have taken the standard AASHTO loads and applied them, but we did go ahead, and we had RWDI on board early on with respect to the crossing anyways. They produced a really good wind climate assessment, and then did a little bit of additional work to really model the bridge in its environment. They created basically a terrain model of the topography of the area, and they modeled both the topography, the hillside, and also the surface roughness that was out there as well. And they simulated then the wind speeds that you could expect at the bridge site. One of the things that was noticed or noticeable in the report was there's predominant bluffs on both the north and south end of the bridge, two main hillsides, if you will, one in each state. And those bluffs really tended to shield the bridge from north-south winds. So we had a very directional wind that was predominantly coming from the west that would affect this bridge. So that helped us to reduce the longitudinal demands on the piers and the forces that they would have to resist. So we ended up reducing the wind speed from 100 miles per hour to 67 in the transverse direction and 58 miles per hour in the longitudinal direction. Now, having sharpened the pencil on the load side of the equation, we needed to go back and address that foundation capacity issue that we still had. We looked at a number of different ways that we could approach that. We looked at strengthening those foundations with either an encasement through cofferdams or potentially with drilled shafts or driven piles exterior, and some sort of a strap footing or tie-in footing to help give that some additional stiffness. But we were really most interested in the soil response and seeing if that would potentially work, because we knew that would be the cheapest solution possible. So we wanted to take a closer look at that. We'll get into that here in a bit. But in order to do that, one of the critical things that we had to overcome was that scour. And if you've worked on any Ohio River bridges, you know that they are very susceptible to scour, in the sense that any kind of scour predictions can be upwards of 20 to 40 feet or even larger in some settings. So that's something that has to be dealt with, and we looked very closely at that. We worked with both KYTC and Indiana, and even consulted with Federal Highway on the scour mitigation for this project. So we looked at, if we were going to reuse those existing foundations, how would we protect them? Well, the idea of a riprap with filter, articulated block mat, and jet grouting all were kind of kicked around, and eventually through consensus with the stakeholders there, the riprap with filter solution was chosen as the best way to proceed forward in terms of mitigating scour. It was the most tried and true, and everybody had the most confidence in it going forward. So we ended up coming up with a refined approach, really, to utilize the soil response, provide a riprap scour counter protection, placing that riprap down below the contraction scour. We ended up at a 12-foot thick mat of riprap. This riprap had a certain gradation which was specified in the contract plans, and it also specified a geotextile in order to make sure that we were able to resist bed forms and able to keep that scour mitigation in place, because ultimately we were going to be relying on that for our soil resistance. So with the soils in place, we had to then see what we could mobilize in terms of that resistance. We created a finite element model using Midas GTS, and that model looks something like this. We had a elastic solid pier modeled. The unreinforced caisson you can see is modeled there. We modeled the soil layer and the rock layer and the interface between the soil and the skin of the unreinforced caisson, this basic standard friction interface, in order to develop what passive resistance we could. We couldn't just come in and say, here's the passive resistance fully developed, because we would have experienced way too much deformation that the structure couldn't handle. So we wanted to get a sense for how much interaction there really was. And this model gave us a lot of hope there. It really ended up reducing the foundation pressures considerably just by having the resistance of that 60 foot of soil up above the rock, even though it was a weaker material. Helped out quite a bit. So to make sure that we weren't all drinking the Kool-Aid, we wanted to make sure that the method was in fact sound. We did a comparison to a classic solution, which was L-pile. We took a 5-foot diameter, 50-foot long drilled shaft, put it in a certain material, soils, and then displaced it. And we did that in both our Midas GTS analysis and in our L-pile analysis, graphed the lateral load versus the deflection, and lo and behold, they were very similar results, almost identical really, which gave us a lot of proof to the method that we were using there, and we felt really good with that validation effort. The other pier response concerns that we had to deal with, besides the foundations, obviously the tension in the stem and the interface between that. We were dealing again with a very lightly reinforced section, and in the case of the unreinforced caisson, no reinforcing. So we had to make sure that we were overcoming that. Essentially, we had turned this spread footer into a giant drilled shaft, if you would, that was now taking flexural loadings. So we had to make sure that we could withstand that. You'll see one of the preliminary engineering reports here that we had with, we had assumed elastomeric bearings in this particular case. We looked at a number of different bearing arrangements, and then we looked at that for all our different strength and extreme load events there. And essentially this is a plot of the tensile stresses that would develop on the extreme fiber of that pier shaft and also of the caisson. And note in particular on the strength 3 case, which is the wind load, how far down that tension goes into that unreinforced caisson. So we had to figure out a way to deal with that. We wanted to make sure that, obviously, since those areas were not inspectable in the future and not accessible in the future, we wanted to make sure that they were well cared for and that there weren't going to be any problems developed. And really, we were kind of outside the bounds of the codes here, because there's really no provisions in AASHTO for taking a pneumatic caisson and reinforcing it after the fact. So we established some criteria to determine to get a 75-year service life, and worked with the two owners in establishing this criteria. The existing pier stems and caissons were basically considered non-reinforced due to the minimal reinforcing in the stems. We did have a conservative look at the concrete strength. We used 7 KSI for that material. We set a limit of 0 PSI tension for any service limit state and 95 PSI tension for all strength and extreme limit states. Again, we felt these were just prudent in order to make sure we had a good performing structure that was able to withstand the test of time. Now, where either of those criteria were not met, the caisson stem had to be strengthened, and strengthening had to be continued past the development length, past that limit of either one of those criteria. As Kevin mentioned earlier, the stem was set up with a minimum encapsulation of 24 inches of high-performance concrete. It was primarily to ensure durability going forward. The preliminary look at the pier strengthening, or the preliminary concept, looked something like this. Essentially, what the plan was to drill holes into the existing caisson. There was a small ledge around there from the stem that would be accessed, drop reinforcing into that caisson and grout it in place, then add stem reinforcing in that 24-inch encapsulation, pour that up, and eventually widen out and form a new pier cap for the wider superstructure. Final step would be to add the scour countermeasure to ensure that the soils remained in place. All this preliminary work had to be documented. We'd come out of this with a good idea of what could be done, and we really needed to convey that now to the design build team so that they had the confidence to also see this solution home. And as Kevin mentioned, that was done in a number of these different criteria documents, the scope of services, special provisions, namely the structural performance criteria and strengthening of the existing piers, were really where this pier work was documented fully. Contract plan details also contained the prescribed scour mitigation that was worked out with both states and federal highway, so that was exactly what was intended to be built out there. Kevin also mentioned those binding project reports. We put so much effort into the vessel collision study and wind engineering study that there really wasn't any need to repeat that. It only had to be updated if you changed the bridge significantly. So those were passed along with the geotechnical overviews. And then we gave all the other informative documents that were generated along the way, including the environmental assessment, hydraulics and scour analysis. Permits. The permits were obtained prior to construction. Many of them were U.S. Coast Guard permit, 401, 404, local FAA and Kentucky Airport Zoning Commission permits, and construction in the floodway. The design build team's responsibilities were really compliance with the permits and then to revise them as needed. If they were to change the solution, if they had to stray from the temporary, we assumed some temporary impacts for construction. If they were to stray or have significantly additional, then they were responsible for amending those as required. And then they also had to obtain a few permits, the Rule 5 erosion control and KYP DES permits. All those were at the contractor's risk with no increase in contract time allowed for permit revisions. Like I said, we helped put the contract out. We helped NDOT ultimately to write the RFP and put together the special provisions and contract plan details. We put together those plans, preliminary plans, and then we were selected by NDOT to stay on as the consultant oversight, doing both design review and construction inspection. And our team was listed here, included CDM Smith, who was the prime for the environmental work. They stayed on for environmental compliance. We added the American Structure Point VS and Test Tech to bolster the inspection, field inspection staff out there. And then we added Pannoni Associates at the request of Indiana to do shop inspection. And Doe Anderson remained on for public involvement. Now, a couple of slides just about our role as far as the consultant oversight. A lot of the role traditionally is just compliance with contract requirements. The unique challenges on this project, being a design build, was really dealing with the buildable units. We had stipulated in the contract requirements a number of different submittals for intermediate, final, and initial submittals as to what those needed to contain with respect to the truss structure only. Everywhere else, the design build team had the ability to define what those hold points were and what was being submitted there. Apologize for that. Construction submittals were a challenge for us on this particular project, and you'll see that when the design team gets into their approach. It'll become a little bit more evident. There were a lot of temporary works on this project, so we had to review those really from the standpoint of safety of the public and safety of the owner, or limiting risk to the owner. The owner wanted to make sure nothing was going to obviously impact the structure, long-term performance negatively. So we looked at it with respect to that and with respect to the public safety. We did not review for means and methods or things like that, and that is a difficult thing to do, to kind of take that hat off and not scrutinize those details as well. So the things like the lifts and slides were really the responsibility of the design build team. We did offer input as it related to performance of the structure or outcomes and effects of the permanent structure, but not as much on the means and methods side. And then the RFP requirements. Obviously, you can't cover everything, and as you think about this project going forward, with the change in MOT that was based on how this group wanted to build the bridge, obviously we couldn't cover everything in a limited document. As far as the construction oversight goes, it was fairly typical for a design build project, and obviously design build projects can be challenging for your team out in the field. A lot of times they're working with partial sets of plans, or information is forthcoming or evolving as the design is still being wrapped up or being changed as the design is evolving. So there was a lot of that to address in the field. That was particularly evident in the shop inspection. Shop drawing revisions were fairly numerous in nature, and there was obviously a rush to get materials ordered and then the details to follow. So that was a challenging part of the project. And then obviously the temporary construction, which you'll see more of that later, but just to give you an idea of the temporary works and what was to be inspected in the field versus not. All of those temporary works are really the responsibility of the contractor per INDOT's standard specifications. So the bulk of what you see in that picture was inspected by the contractor. The permanent works, being the concrete pier in the center, is really what the primary focus was for our inspection team. We were out there more in an observation role for the temporary works, just making sure that it was being built per plan, but not necessarily checking every bolt and everything like that. As far as the lessons learned for this particular project, I think one of the things that I've learned about design build is buildable units matter. I tend to refer to it as buildable unit soup. Anything that can be pulled together out of that soup and make a word or make a submittal sometimes is the mode of going forward, just to get a package approved and out the door. So it may behoove an owner to work early on, get the design build team to set up a schedule, and then stick to that schedule. Would probably be the easiest thing for everybody to go forward. Same but different. You want to try to accommodate as many new ideas as you can in a project like this. You really want to be open to ideas that aren't affecting the end-all performance of the structure. So that's something to keep in mind as you go. Changes is a good thing. Major changes like we had in this one, where they proposed an entirely new maintenance traffic scheme. And when something like that happens on your project, you might want to take a time, stop. Those are deserving of reconsideration, especially where contract milestones or requirements or for incentives and damages. All those kind of things should be perhaps rethought out and renegotiated when you get a major change in proposal like that. RFIs, if you're writing a RFP, you definitely need to address that. They're going to be there, they're coming, and you better be ready for them and better have a plan to address them in a timely fashion. And then document controls are extremely important, so make sure that you're geared up for that as well. And with that, I'll open it up to any questions you all may have.
Thank you, Aaron. Great presentation. We'll now begin the Q&A session, and we've received a couple of questions. And first, could you talk a little bit more about the 24-inch encasement of the piers and why that was required?
Yeah, certainly. The 24-inch encapsulation was not so much required by design as it was for durability. Again, going back to the CTL reports, there were issues with the erosion of the paste and even erosion of the aggregates in the existing concrete. So we wanted to protect that from the Ohio. So an encasement was warranted. But part of that is we were really dealing with trying to get this bridge to last for 75 years, and it could have been argued during the process that either you could have done it a number of different ways. You could have had a 1 foot thick encapsulation. You could add a 2 foot thick encapsulation, and it would be difficult to gauge serviceability going forward. So in order to level the playing field and get everybody bidding the same thing, a 2-foot thick encapsulation was specified and not deviated from.
Okay, thank you. We're now at the end of the second 40-minute module. Thanks again to Aaron Stover and to all who participated in the second module. And again, if your question wasn't answered, please feel free to contact Aaron directly.